It's really quite wild how these AI tools like ChatGPT, Gemini, DeepSeek, they just seem to get what you're asking, almost
Mhm.
like mind reading.
Right. It feels like that sometimes.
But have you ever stopped to think about what's actually going on under the hood, how they understand? Turns out, a really, really fundamental piece is this thing called embeddings.
That's absolutely the key. These large language models, they aren't just looking at words as, sequences of letters. They're working with numerical representations. That's what embeddings are all about.
Exactly. So for this deep dive, we thought we'd really dig into this concept. Embeddings.
Yeah.
The sources we looked at give a great view, what they are, why they're so important, the different types, how they've evolved, and even some of the challenges.
Right, the complexities too.
So our mission here, for you listening, is to get a clear handle on this really foundational AI concept,
Yeah.
hopefully without making your head spin with too much jargon.
Exactly. We want you to walk away feeling like you've got a solid, practical grasp of embeddings.
Okay, let's jump in then. What exactly are embeddings? Laid out for us.
Okay, so think of embeddings simply as a way to translate things, words, sentences, even pictures, into lists of numbers.
Lists of numbers, like coordinates.
Sort of, yeah. We call them vectors. And the really clever part is that these vectors live in a kind of high-dimensional map, a vector space.
A map.
Yeah, a space where things that have similar meanings or similar characteristics are positioned closer together on the map.
Ah, okay. So instead of raw text or like a million pixels for an image, we turn it all into these numerical lists that computers can actually crunch.
Precisely. Embeddings take complex, often very high-dimensional data. Think of all the nuances in language or the detail in a photo, and they condense it down into these lower-dimensional vectors.
Lower dimensional, meaning fewer numbers in the list.
Exactly. It makes it much more manageable for the AI models. It's like summarizing the essence of the data in a numerical form that these models, which fundamentally operate on numbers, can easily process and learn from.
You mentioned vectors earlier, like a single number A or two numbers A, B. Is that the basic idea?
That's the core concept, yeah. A single number is a 1D vector. Two numbers give you 2D. And embeddings usually have hundreds of dimensions.
Hundreds, wow.
Yeah, and what's really cool is that these vectors have mathematical properties. You can actually do arithmetic with them.
Arithmetic. Like adding word meanings.
Kind of. So if you have an embedding of vector for king and subtract the vector for man, then add the vector for women, the resulting vector is often incredibly close to the vector for queen.
Whoa. Okay, that's not just closeness, that's like capturing relationships.
Exactly. It shows that the structure of the vector space, the directions and distances between these points, actually encodes semantic relationships. It's pretty powerful stuff.
Okay, so we're turning data into these meaning-packed vectors. But you said words, sentences, images. They can't all use the same kind of embedding, can they?
Good point. No, you need different approaches for different data types. Let's start with word embeddings. This is probably the most classic example.
Okay.
Here, each individual word gets its own vector. And like we said, in the vector space, words that are used similarly or mean similar things end up close together.
So cat and dog might be near each other and maybe closer to pet than to, say, car.
Precisely. And as the king, man plus woman example shows, it captures more than just simple closeness. It gets at analogies and relationships.
That really illustrates it well. What were some of the big models for creating these word embeddings?
Some of the real foundational ones you hear about are Word2Vec, Glove, and Fast Text. They were pioneers in figuring out how to do this effectively for individual words.
Got it. Word2Vec, glove, fast text. So that's words. What about whole sentences? How do you capture the meaning of an entire sentence in one vector? That sounds harder.
It is a bit more complex. For sentence embeddings, the goal is exactly that. Map a whole sentence to a single vector. The principle holds, those sentences with similar meanings should result in vectors that are near each other in the space.
So it's like a numerical summary of the sentence's meaning.
Exactly. You're condensing the overall semantic content. Models like Infercent or Doc2Vec, which, as the name suggests, can even handle whole documents, were developed for this. Useful for things like finding duplicate questions or summarizing text.
Right. So the weather is lovely today, and it's a beautiful day outside. Should have similar sentence embeddings.
They should, yes. Okay, moving on. Image embeddings. How do we get a vector from a picture?
Yeah, that seems like a totally different beast. Images are visual, not linguistic.
They are. And the go-to technology here is usually convolutional neural networks, or CNNs.
CNNs, right. Heard of those. They're good at image recognition.
Exactly. CNNs are designed to automatically learn and identify important visual features in an image, edges, textures, shapes, objects, that kind of thing. These learned features are then essentially compiled into the final image embedding vector.
And what's the use case there? Finding similar images.
That's a big one. Image classification, figuring out what's in the picture is another. And yeah, content-based image retrieval, like finding visually similar products online or reverse image search.
So if I search with an image of a chair, it uses the embedding to find other visually similar chairs.
That's the idea. And then finally, we also have audio and speech embeddings.
Okay, so sound waves into vectors.
Pretty much. Raw audio data, or transcribed speech, gets converted into vector representations. These can capture different things, maybe the actual words spoken, the speaker's voice characteristics, or even the emotion in their voice.
Emotion detection from audio. That's fascinating.
Yeah, it has applications there. Models like VG-GISH or Wave2Vec are used in this space, powering things like speech recognition systems, speaker identification, and, yes, potentially emotion analysis.
It's amazing how this one core idea, embeddings, applies across text, images, audio. But maybe step back a bit. Why did we need embeddings in the first place? What was wrong with, I don't know, just feeding raw words into a computer?
That's a really important question. The problem is that most machine learning models need numerical input. Raw text, or categories like cat, dog, fish, they aren't numbers.
So how did people handle that before embeddings?
A common early technique, especially for categorical data like words, was one-hot encoding.
One hot.
Yeah, imagine you have a tiny vocabulary. Cat, dog, fish, bird, horse. 5 words. For each word, you create a vector that's all zeros except for a single 1 at the position corresponding to that word.
Okay, so cat is 1, 0, 0, 0. Dog is 0, 1, 0, 0, 0, like that.
Exactly. Each word gets a unique binary fingerprint.
Seems simple enough.
It is for 5 words. But what happens when your vocabulary has, say, 50,000 words, which is pretty standard for English?
Uh-oh. Then each vector is 50,000 numbers long, and almost all of them are zeros.
Precisely. You get these incredibly long, incredibly sparse vectors, sparse meaning mostly zeros.
That sounds inefficient.
Very inefficient computationally. But worse than that, it provides no sense of relationship between words. In a one-hot system, the vector for cat is just as different from dog as it is from car or democracy. There's no concept of semantic similarity built in.
Right, because each one is in a totally different spot. No overlap, no shared features.
Exactly. The model treats every word as an isolated entity. This makes it really hard for models to generalize or understand nuances.
So embeddings solve this how? By being dense.
Yes, that's a key difference. Embeddings are dense vectors. Instead of 50,000 dimensions with mostly zeros, you might have, say, 300 dimensions, and most of those numbers will have non-zero values.
Okay, so they're shorter and packed with numbers.
Packed with meaningful numbers, that's the crucial part. The process of creating embeddings learns values for these dimensions, such that the distance between vectors reflects the semantic relationship between the original items.
Back to the closeness idea. Similar words get vectors that are close together in this dense lower dimensional space.
You got it. It introduces this geometric representation of meaning, and we can measure that closeness.
How do you measure it? Is it just like standard distance?
There are a few common ways. Cosine similarity is very popular. It measures the angle between two vectors. If the angle is small, they point in a similar direction, meaning they're semantically similar.
Angle, okay. Not just distance.
Right. You can also use Euclidean distance. That's the straight line distance you'd normally think of. Or Manhattan distance, which is like measuring distance if you could only travel along grid lines. Cosine similarity is often preferred because it focuses on orientation rather than magnitude, which can be useful for text.
Okay, that makes a lot of sense. Dense vectors, meaningful distances. It paints a much clearer picture of why embeddings are so useful.
Yeah.
So where are we seeing the biggest impact of these in, real-world applications?
Oh, they're everywhere now, really foundational. Especially in natural language processing, recommendation engines, computer vision, basically any way you need to encode complex relationships, semantic, contextual, behavioral, in a way machines can use.
Give us some top examples, text search.
Definitely. In text search, embeddings let you find documents relevant to your query even if they don't contain the exact keywords. You embed the query, embed the documents, and find the documents whose embeddings are closest to the query embedding.
Understanding the meaning behind the search, not just the words.
Exactly. And this is super important for things like retrieval augmented generation, RAG.
AirG, right? That helps stop LLMs from just making stuff up.
Kind of, yeah. RAG uses embeddings to find relevant factual documents first, and then feeds that information to the language model along with the original prompt. This helps ground the LLM's answer in real data, reducing hallucinations. Embeddings are the key to finding that relevant information efficiently.
That's a huge application. What about recommendation systems like Netflix or Amazon?
Absolutely critical there. Items, movies, products, songs, whatever get embedded based on their features and also how users interact with them. Your user profile might also be represented as an embedding in the same space.
So it recommends items whose embeddings are close to my embedding.
Pretty much, or close to the embeddings of things you've liked before. It's all about finding similar vectors, whether it's user-to-item similarity or item-to-item similarity.
Explains why it sometimes feels spookily accurate.
Yeah.
One more sentiment analysis.
Yep. Embeddings help capture the features related to sentiment. Words or even whole sentences that express positivity tend to cluster together in the embedding space, separate from those expressing negativity.
So the model learns to distinguish positive, negative based on where the embedding falls in that space.
Exactly. The position and neighborhood of the embedding carry the sentiment signal.
Okay, really concrete uses. Now, you mentioned earlier that these models evolve. We started with one hot then?
Yeah.
Where did it go from there?
Right. It's been quite a journey. So one hot encoding was, well, basic, very limited.
Just ones and arrows, no meaning.
Right. Then came techniques like TF, IDF, term frequency, inverse document frequency. This was an attempt to weigh words based on importance.
How did that work?
It looked at how often a word appears in a specific document, term frequency, compared to how often it appears across all documents, inverse document frequency. The idea was that words frequent in one document but rare overall are probably important descriptors of that document.
Okay, so it added some intelligence, trying to find significant words.
It did. It was a step up, developed way back, actually. People like Karen Spurk-Jones were pioneers. But TF-IDF still fundamentally couldn't capture semantics. Car and automobile were still just treated as distinct strings unless they happened to appear in similar documents. The meaning wasn't there.
Still missing that core understanding. So the breakthrough was?
Word2Vec. Around 2013, Tomas Mikhailov and his team at Google published this. It was revolutionary.
What made it so different?
It used a shallow neural network trained on vast amounts of text, specifically to learn vector representations of words based on their context. The key insight was that words appearing in similar contexts likely have similar meanings.
Learning from context.
Exactly. Word2Vec produced those dense embeddings, usually a few hundred dimensions, where distance, often measured by cosine similarity, indicated semantic closeness. This was the first time we really got good, general-purpose word meaning captured numerically.
That sounds like the start of the modern era of embeddings.
It really was. Word2Vec, along with Glove from Stanford and FastText from Facebook, represent this wave of static embedding models.
Static. What does that mean?
It means each word gets one fixed vector representation regardless of how it's used in a sentence. So the word bank has the same vector whether you're talking about a river bank or a financial bank.
Ah, I see the limitation there immediately. Words have multiple meanings. Polysemy.
Exactly. That's the big drawback of static embeddings. They're great for capturing general meaning, like king is related to queen, but they struggle with words that change meaning based on context. The single vector for bank is sort of an average of all its meanings, losing the specific nuance.
Because it just looks at general co-occurrence patterns, not the specific sentence structure.
Right. It relies on patterns within a fixed window of surrounding words, averaged over the whole training corpus. This limitation paved the way for the next big leap, contextualized embedding models.
Contextualized, meaning the embedding changes based on context.
Precisely. And the landmark model here, the one that really changed the game, was BERT.
BERT. Bidirectional encoder representations from transformers. We hear that acronym a lot.
You do, for good reason. BERT, developed by Google, uses the transformer architecture, which is key. But its major innovation for embeddings was being bidirectional.
Bidirectional. Looking both ways.
Exactly. Unlike earlier models that might process text sequentially, left to right or right to left, BERT looks at the entire sentence at once, considering both the left and right context simultaneously to determine the meaning and thus the embedding of each word.
So the embedding for bank in riverbank is generated considering river, and the embedding for bank in money in the bank considers money.
That's the core idea. BERT produces contextual embeddings. The same word can have different vector representations depending on the sentence it's in. This allows it to capture that nuance, that polysemy, that static models missed.
That sounds much more like how humans understand language. Context is everything.
It's a huge step closer, yes. This ability to retain contextualized semantics is what made BERT and subsequent transformer-based models like GPT so incredibly powerful for almost all NLP tasks.
Wow. Okay, so quick recap. One hot, basic, sparse, TF-IDF, word importance, still no semantics. Word-to-vec glove, static embeddings, general semantics, context blind. BERT, contextual embeddings, understands nuance. Quite an evolution.
A very rapid and impactful one, yes. And it's still ongoing.
Now, this all sounds amazing, but are there downsides, challenges, limitations we need to be aware of?
Absolutely. Like any powerful technology, embedding models come with significant challenges, especially concerning ethical considerations.
Ethics. How so?
Well, these models learn from massive amounts of text data, usually scraped from the internet. And what does that data contain?
Pretty much everything humans have ever written online, including all our biases.
Exactly. Human language is riddled with societal biases, gender stereotypes, racial prejudices, you name it. And if the training data is biased, the embedding models will learn those biases.
So the geometry of the vector space itself can become biased.
Precisely. The classic example is finding that the vector for man is closer to doctor, while woman is closer to nurse, purely based on historical text associations, not inherent truth. Or certain names being associated more closely with negative or positive concepts.
And that bias then gets baked into any application using those embeddings, like hiring tools or recommendation systems.
That's the danger. Biased embeddings can lead to unfair, discriminatory outcomes in downstream applications. A search engine might surface stereotypical results. A resume screening tool might unfairly penalize certain groups.
That's a serious problem. What can be done about it?
It's an active area of research. There are techniques for debiasing embeddings trying to identify and mathematically remove or neutralize dimensions in the vector space that correlate with known biases.
Trying to unlearn the prejudice.
Sort of. It's complex. But it also involved careful curation of training data, making it more diverse and representative, and rigorous testing of models for bias and fairness before deployment. It's an ongoing responsibility.
Definitely sounds critical. Any other major challenges?
Another big one is transparency and accountability. Especially with these huge, complex models like BERT or GPT, the embeddings they produce have hundreds, sometimes thousands of dimensions.
Right, you said hundreds earlier. Hard to visualize.
Exactly. They become black boxes. We know they work, often remarkably well, but it's very difficult to inspect an embedding vector with 768 dimensions and understand why it represents a certain meaning or why the model made a particular decision based on it.
So if something goes wrong, or if there's an unexpected bias, it's hard to pinpoint the cause within the embedding itself.
It can be very challenging. This lack of interpretability makes debugging difficult and raises questions about accountability when AI systems make mistakes. There's a need for more transparency from developers about the data used, the model choices made, and the potential limitations.
Bias and black boxes, definitely crucial things to keep in mind.
They really are. Building and deploying these technologies responsibly requires constant attention to these issues.
Well, this has been incredibly illuminating. It's clear that embeddings, despite the challenges, are just a cornerstone of modern AI. They've unlocked the ability to process this high-dimensional data, text, images, audio in ways that just weren't possible before.
Absolutely. From the early days of Word2Vec and Glove to the contextual powerhouses like BERT and the models that followed, they've driven so much progress in NLP, computer vision, search, recommendations. The list goes on.
And it feels like understanding them, even at this level, is becoming increasingly important for anyone working with or even just using AI.
I completely agree. As these models continue to evolve and shape more aspects of our world, knowing how they represent meaning is key. It empowers you to think critically about AI capabilities and limitations.
And maybe even to build more powerful, fairer systems yourself. Understanding the foundations is the first step.
Couldn't have said it better.
So a final thought for everyone listening. As you see AI interpreting your requests or suggesting content, think about those underlying vectors. Consider the implications of machines learning meaning through geometric relationships. Where might this technology go next, and what new possibilities or new challenges might arise as our ability to embed meaning continues to advance? Definitely something to ponder.
A great question to leave with. It really underscores the ongoing journey in understanding intelligence itself, both human and artificial.